Hi, in this video we will learn how the rank of matrices can play a role in determining how many solutions a system of linear equations have. Let us recall that when we had a system of linear equations of the form ax equals to b, then we found the augmented matrix, and while this augmented matrix, we row reduced it to row reduced echelon form. And then using the leading number of leading was and different information about this row reduced echelon form, we were able to determine what are the cases for these solutions of this system. For example, if we had a row which was 0 on the left hand side and the non-zero on the right hand side, then we had no solution, which we called it inconsistent or no solution. Okay, and well, if this didn't happen, we called it consistent, meaning that there are solutions for this system, either unique solution or infinitely many solutions. So how did we know that we have unique solution or infinitely many? Well, if the number of leading ones was equal to number of columns. In other words, every column of A had a leading one. Yes. So in that case, we had unique solution. If the number of leading ones were less than number of columns of A, then, we had infinitely many solutions. Now you see that we are talking about leading ones here, and leading ones in the row reduced echelon form is equal to rank. So it means that, there is something we can do a little bit more here and turn all these cases and write them in terms of rank. Well, let's start with the inconsistent case. If we row reduce augmented matrix and we end up with this case. So on the left, then we count the number of, let me write it here, yes, rank of number of leading ones, which is already in the row reduced echelon form of A. And then you can consider the matrix AB. So I added the right column B to A. And then, since we have a non-zero entry here, it means that if I ignore the separating line and continue making reducing further, I can generate next leading one out of this non-zero entry. In that case, it means that the rank of the matrix AB will be definitely bigger than rank of A. Okay, so if the rank of AB is bigger than rank of A, we are done. We have no solution. Well, if that doesn't happen, first thing first, rank of A is equal to rank of AB. That's the first thing. Now, here, number of leading ones is rank of A, and number of columns, let me just write the number of columns. So if we have rank of AB equal to rank of A and then equal to columns of A, then we will have unique solution. And if we have rank of AB equal to rank of A, and less than number of columns of A, then we have no solution. Sorry, infinitely many solutions. Okay, let's see these things in practice. I have some examples here for you. Okay, we can solve these examples as the regular Gauss-Jordan elimination method, but here I want to use this rank thing to determine how many solutions we have. Okay, so here we start with the augmented matrix 2 1 1 1 3 0, and then we row reduce it. Okay, I won't do this guy in full steps, but what you can see that if you complete this, you will get to this -1/5. And what does this have for us? First of all, the rank of this matrix is equal to rank of A is equal to 2. How about rank of AB? Well, if you look at AB, there are only 2 non-zero rows here, and it's already row echelon form, and this is also equal to 2. And then how many columns A have? So the number of columns of A is equal to 2. There are 2 columns. So you see that rank of AB is equal to the number of columns. So it means that we have unique solution. This is how we were able to figure out how many solutions we have for row using the Gauss Jordan elimination method. But here also you can use the ranks. Okay, this guy has this augmented matrix 1 0 1 1 0 1 -1 -1, and here 2 1 1 2. You can row reduce it. I have done this before, so you need to do your work. This is our homeworks. Here's it gets 0 0 -1. In this case I'm row reducing the whole matrix AB. And now you see that rank of matrix A, just consider this part. We have 2 non-zero rows. Rank of AB, so rank of AB, so consider the whole matrix. We have 1 non-zero row, 2 non-zero rows, and 3 non-zero rows. So this is 3. These two are not equal. And if you look at the table we had up there, if these are not equal, or this guy is bigger than the other one, then that means that we have no solution. So this is inconsistent. Yeah. For this last one, we have the augmented matrix 0 0 1 2 0 2 4 -2 0 0, and 2 4 -1 2 0. Row reduce it, and as I said, I've done this before. You will get into this matrix. And now, rank of A is equal to what? So we have only 2 non-zero rows. Rank of AB, we have, again, you ignore this line here, separating line. You see there are only exactly two non-zero rows. So this is again equal to this. But how about the number of columns of A? Number of columns of A. So let me put this separating line back. So we have 1, 2, 3, 4. So this is equal to 4. And as you can see, this is bigger than that. So this means that the rank A, rank AB are equal. This means consistent. And then when it is consistent and the number of columns is bigger than the rank, then we have infinitely many solutions. So this gives you just an idea that, okay, how I can translate different things that I knew before in terms of the rank. We will proceed and do a little bit more things in the same way. Let me finish this video with 2 remarks. Remark 1 says that, okay, so you see that when we try to find rank of any matrix, so rank of matrix B, let me write it as capital B. This is number of leading ones in row reduced echelon form, but number of leading ones in row reduced echelon form or number of non-zero rows in row reduced echelon form cannot get bigger than the number of rows of B. Also, we know that every column can contain at most one leading one. It means what? It means that the number of leading ones in the row reduced echelon form of B cannot go beyond number of columns of B. So rank is always less than the number of columns and less than number of rows of that matrix. That's first thing. And then another remark, which is very nice, easy to understand, but we will use, you'll see how it will go. So we were talking about the rank of a matrix A, and then we added one column to this matrix. By adding a column to matrix, at most you can generate one extra leading one when you're doing row reduction. So it means what? It means that let me write this one this way. Rank of AB, the matrix AB, can be either equal to rank of A, or it can be at most one more than rank of A. It cannot be two more because we added only one column, and that column at most will have one new leading one. So it cannot go beyond. It cannot have two leading ones. So the rank of AB cannot be bigger than rank of A plus 1. It either be rank of A or rank of A plus B. We will use these remarks when we do more examples for these topics.